These notes will help prepare you for homework number 2. And the goal of homework number 2 is that you're able to handle problems with F equals ma with Newton's second law where the forces are not all along the perpendicular axes, but some of them may be tilted like this. This video is a lot easier if you can print out the notes handout that goes with it that's in the topics, force and Newton's laws. And to make it easier still, I've made 2 videos. This is for the first part of that handout, and then there'll be another video for the second part. All right, here's some preliminary trick, just to review and to show you how what you already know leads to what you need in order to do these kind of problems. You should pause the video and try to fill in the boxes, fill in the blanks. And I'm going to go much faster than I would in a normal classroom because I know you can pause the video at any time and copy things down or rewind it. Right, so obviously sine is B over C. This is A over C. But we're not going to use them like this. What we're interested in is how long side A is and how long side B is. So we solve these, and we get C, and you should pause it, make sure you get this right on your own. C sine of theta and C cosine theta. You want to think this way from now on in this chapter, of this, the adjacent side being hypotenuse times cosine theta, and this, the opposite side, being hypotenuse times sine theta, like that. In fact, I will frequently call this the cosine side and this the sine side. Okay, so here I ask you to do it with actual numbers. And notice I've written the formal, like official way this could be phrased in a book or in a college class. You're being asked to resolve the vector f into its ij components. Now I want to say just a little bit about that vocabulary. Resolve here means to break up. It doesn't mean to like make a New Year's resolution. It means to break up. And you've seen that use of solve before in the word dissolve, like when you dissolve salt into water and it breaks up into its ions. And the components are literally from Latin, the things that are being put, that's what that means, together. The components, the I component and the J component, you put them together and you get the original vector. Now, if you're into astronomy or optics, you've actually seen the word resolve this way to mean break up. Because if you're looking through a weak telescope and you see this blur, and you get a better telescope, it can resolve that blur so that you see it's actually 2 stars. It's not a single star, it's 2 stars. The telescope is resolving what it sees into the 2 stars, and we say the telescope has a stronger resolution. All right, so back to our class. Resolve the force into its ij components. So you draw the same kind of picture you had here. And beginning students often do this and stop. That's not a good idea. It can lead to problems and wrong answers. These are supposed to be vectors. This black vector points up and to the right. That's the original one. So I should draw a vector pointing to the right and a vector pointing up. And notice the components will always be at a right angle because one's I and one's J. If you ever resolve a vector and your components are not at a right angle, you've been misled by the diagram and you're going to make a mistake. All right, so it says resolve them into components, but I want to know how strong this component is and how strong a force that component is. So I do what I had here. You want to do that, pause the video and try to do that your own. Figure out what should go here and what should go here. Okay? This would be 100 times the cosine of 20 degrees because it's the adjacent side. And this would be 100 times the sine of 20 degrees. And when you put that in your calculator, make sure it's set to degrees, you get 94 newtons here and 34 newtons here. And you should have done that on your own to make sure you get that. Okay, I want to say one thing very quickly. Because it's a right triangle, because the real world vector, the real force is always the hypotenuse, these 2 sides will never be bigger than the real vector. Your components, each of them individually, will always be smaller than the original vector. So we've got that 94 because that's in the direction it's more the vector lies here. This is more right than up. Right, in 34. Okay? I also want to say one more thing. The I vector is not always cosine. It's not like math class where you define everything from here. If the angle had been defined differently, for instance, if it had been 70 degrees here, these trig functions would be reversed, and you'd have this side using cosine. So it goes with the diagram. You have to read each diagram fresh and think. You cannot assume that the I vector always is going to have cosine. Okay, here it is in letters. Same question. It says resolve f into its components along the xy axes, like the usual horizontal and vertical axes. So let's do that. You should pause the video and try to do it on your own. Your answer will have only letters. So there's the I component, there's the J component, and of course this will be f cosine theta, and this will be f sine theta. And that's it. It's done. Now I'll show you how we use this to do a problem. This is a problem like 1 or 2 in the homework. And this is in that handout. If you're following along in the handout, this is exactly the same problem. This would be the situation of, say, a toy wagon on a floor. There's no friction, so the wagon has wheels that are very, very good. And a child is pulling with a force of 20 Newton on the wagon's handle up at 60 degrees from the horizontal. Your first question might be, well, wouldn't that be enough to lift the wagon off the ground? But you're going to do a quick check. Gravity would be 30 Newtons down. There's no way 20 Newtons can lift it. Even if it were vertical, it wouldn't lift it. Okay, and then the question is asking you to do 2 things. Find the value and direction of the acceleration, and find the value of the normal force. You have to use common sense and think, okay, it's a wagon. Which direction would the acceleration be? This is the force on it. You should see right away it's going to be horizontally. And if you don't see that, we'll draw a force diagram. Now I'm going to go through how to solve this. We did not have any problems like this in freshman year because we have a force at an angle. So since this is new to you, as I go through and solve it, I'm going to number the steps. The first step, as you might think, it's a problem with forces, and we're using F equals ma to find the acceleration. So the first step is to draw a force diagram. That's why we did that huge packet. So you could handle just about any force diagram you have to in this class. So you should pause the video and do that yourself. Gravity down, and on a force diagram you want to draw arrows, labels, and then numbers if you know them. I know gravity's 30. It's on a flat surface, so normal force up, Fn. Now, is the value of Fn equal to 30? You should pause the video and think about that, and the answer is definitely not, no, because this force is also here. This object has 3 forces on it, including this handle force. This handle force, wait, it's at an angle, but think of how you would describe this using words right, or up, down, right, and left. You would describe it as right and up. So this has an up part that's pretty significant because that's 60 degrees. So this does not have to be 30. It's going to be less than 30. It's going to make up the difference, 30 minus whatever this is. Okay, 2. The next is something we did not do in freshman year. We drew force diagrams, but we did not do the next step in freshman year. If you try to find the acceleration from this, it's going to be kind of nasty. This at an angle here, I don't even want to get into how you would do this without resolving this vector into components. So I'm going to tell you a kind of 2-step process here. The first step is choose your axes. And you might think, well, wait, choose axes. Isn't it just always x and y? And the answer is it's definitely not x and y. And you'll see that in the, not always. It's definitely not always x and y, and you'll see that in the next video. What's our rule for how to choose axes in these problems? I actually said it earlier. And the answer is you choose the axes so that the acceleration vector points entirely along one axis. And here you can see the acceleration is going to be to the right. So you choose axes so A is along an axis. Here, you're lucky. The acceleration is going to be that way because there's not enough force to lift this thing off the ground. So the acceleration is going to be that way, so I can choose my usual horizontal and vertical axes. Okay? Then, step 3, and let me make sure you can see everything. Good, yes. Okay, step 3 is to realize you cannot use this diagram to solve the problem because you have a vector at a problem. You have a problem vector that's at an angle with the axes. So you resolve, step 3 is to resolve vectors not on an axis. Gravity's along an axis, normal's along an axis, they're your friends, they're fine, you don't have to resolve them. But this handle force is not along an axis, it's at an angle, so we have to resolve it. I can get to that started here. It's clearly right and up, so I draw a vector pointing right, I draw a vector pointing up. These two have to be at right angles, the I and the J. Could I figure out how strong each one is? And the answer is yes, of course. I'm not going to go through those steps because I know you can do it. And I like to add it to the force diagram in a different color or with dotted lines. If you draw them the same as this, or the same as your other forces, you can get misled and think this thing now has 5 forces on it. Gravity, normal force, the black one pointing that way, the green to the right, and the green up, and that's absolutely wrong. These 2 green ones replace the black one. You could erase them at this point if you like to do that, but I'm going to show you what I learned from an engineering book, and that's to draw what's called a working diagram. And what a working diagram is you draw any forces, you draw every force that's along an axis. So if any force is already along an axis, you draw it. Fg equals 30, Fn. But any force here that was a problem at an angle to an axis, you don't draw it. You draw its components. Okay? You don't draw the tilted force. Since the tilted force is equivalent to the 2 green ones that do point along axes, you draw them. So I would draw this force this way and this one this way. And as I said, this is 20 times the cosine of 60, etc. We can figure out what those are. I'm not going to do all that on the board. You can use a calculator to figure that out. Okay? I rounded this at 17.3, but I rounded it. So you would get that from using the cosine of 60 degrees. This now becomes your working diagram, which means you use it to work from. And as soon as you've got a working diagram, it's not a bad idea to cover up the original. I'm actually going to erase it. You can, of course, look at it in the video by backing up. But I'm going to erase it so it doesn't distract us. Now we solve the problem using this. And look, and we'll draw the mass in here. The answers just jump out at you. Once you've got a working diagram, the answers just jump out at you. So we know that the wagon's not going to accelerate up or down. So we know these up and down forces have to balance. So just look at that. You can immediately see, without doing any equations, what Fn has to be. So, right, so Fn, you should pause the video and try it yourself. Right, well, we've got 30 newtons down. We need 30 newtons up to keep this thing having no acceleration up and down. It's only going to move sideways. So Fn has to be 13 newtons. And then you say, well, what's the acceleration going to be? That's the other question. The acceleration is in this direction. And so only forces in this direction matter, and there's only that. We got a force, and we got a mass. We can figure out the acceleration, and you get that the acceleration is 3.3 meters per second squared. And you could put an arrow to the right, or you could put 3.3 meters per second squared I if you want, or you could write the words to the right. So we'll sum up. You draw a force diagram, you choose your axis, so A is a long one axis. This may be the trickiest part for you, to think about that. And for that, you have to use your real-world common sense. Then if there are any vectors that are a problem because they're at an angle to the axes you chose, you resolve those into their parts, and then you draw their components, their parts, on your working diagram. And you leave out, we never draw that one that's tilted. Once you've drawn a working diagram, the problem becomes easy. You use the working diagram, and a lot of the times the answers will just jump out at you. We get that.